Today I want to talk about this phenomenon that I have been seeing around me that deserves more attention. It's this phenomenon of being optimal on paper and therefore being broken in reality. And it's kind of a general story. We have this idea that we have like an analytics translator. It's kind of a role within the company. And then the very common question is something like, well, we have an actual problem. We will turn that into an analytical problem. We add a little bit of data into the mix. Maybe we do some stuff with algorithms, right? And then we have this analytical problem, and we can say we have a 10% boost. Yay, we're doing the good thing. We're solving an issue here. But what often gets forgotten is that you still did the translation in this direction, which means that at some point you're also going to have to make a translation back into the other direction, and you could wonder if that 10% boost in your analytical domain actually translates back, because there's bound to be some form of translation sort of error happening here. And I fear that it's getting a little bit too easy to look at that 10% boost and go, ooh, I'm doing the good thing, while ignoring all the translation errors that are happening at the same time. And the way I would like to describe that is something can be optimal on paper and broken in reality. And I think the more attention that you pay to it, the more that you're going to see it. And this is especially true in the domain of model benchmarking. So what I would like to do now as a first demo is just show you a benchmark, and we'll see what goes wrong. That's going to be the idea. So I've got this Jupyter notebook, and also just for context, I work at this company called Rasa. We are building open source software to build virtual assistants and chatbots, so lots of NLP, that's kind of my domain. So I figured, what might be a common task? Well, maybe we would like to evaluate which embeddings are good for virtual assistants. So for those of you that are a little bit less familiar, don't worry too much about it. Embedding is basically a thing where text goes in and some array of numbers comes out, and hopefully that array of numbers is somehow a proxy for the meaning of the text that came in. It doesn't actually work like that, but it's good enough, just we have an array of numbers. And I was kind of curious, well, let's take text that represents an intent. So buy me a pizza. Okay, then the intent is you want to purchase something. What's the time? Okay, then I want to know what time it is. And I have this data set with 150 intents. Each intent has 150 examples in it. And I figured, let's try out a couple of pipelines. One thing so the basic pipeline is text goes in, every word is getting indexed, and every word is then a feature in the pipeline. So for every word, we're going to calculate the weight to figure out how much that's going to influence the label. Then we also have the same thing, but for subwords. And then we have the thing where we do the checking with the embeddings. We have one embedding that comes from Meta, Facebook, called FastText. They trained a system. And there's another thing based on sort of a more BERT kind of model called the Universal Sentence Encoder, and that is from Google. Again, the whole point of this exercise is that we're hopefully going to learn something that's general about chatbots, because it would be kind of nice if we could measure if there's a difference between fast text and the Universal Sentence Encoder. Okay, so this is the pipeline, right? And the only thing I'll be changing to this pipeline is just this one embedding. I'm going to flip out the fast text. I'm going to flip out the Universal Sentence Encoder. Okay, if this was like a benchmark that you might see in an academic paper, then probably the end result is something like this. You'll see a table, right? And I'll zoom in just a little bit to make it just a bit bigger. But you might see a table like this. Like the fast text has an accuracy of not 91, and the other one's not 92. All right, Universal Sentence Encoder, that's better. Now, if this is a good article, something that's a little bit more focused towards like industry and practice, I would argue you would also list the prediction time. And one of the things that you would see here is that the Universal Sentence Encoder is like a factor more than 10 slower, just to compute, basically. It's okay, so far so good, but you can still, call it a win because, oh man, we have a higher number. And this is common, right? We've all seen these situations where one model has a higher number than the other one. But let's now dive into all the things that may go wrong here, because I think that there's a bit of a farce in the background. The first one is that we are not asking how many data points we're actually basing this number on. Because if we now pretend that this is an A/B test, right, and we do the beta distribution trick, I could say, well, there's 4,000 examples in my test set, so there's also like a confidence interval around this number, right? I should probably make that plot. So here's the beta distribution trick, and here's the plot that you might get. Fast text has a number, but it has a certainty bounds around it. Universal Sentence Encoder, same thing, also has a certainty bounds around it. And if you look at it this way, instead of just looking at that one number, you do kind of go, gee, there's a bit of overlap between those two distributions, right? It's not that clear anymore that one number is actually larger than the other one. And if you were to really formalize this into like a hypothesis test, you could kind of say, well, the number here is not 8.5. Usually people like not 9.5 instead. So am I really that convinced that this one model is better? Maybe not. The thing that I find a bit interesting and tricky about this is I think it's not a common industry practice to do this. A lot of people really like to look at the one number, but I would hopefully you all agree that, yeah, there's also this uncertainty bound around it. And if I have a way simpler model that's very light, this can be a great argument to your colleagues to say, well, we can still use a light model because the confidence bounds don't guarantee that the other model is actually way better. This can be a great way to keep your systems light in practice. I would love to see it more. But this is not even the worst thing that happened in our benchmark. Because you see, if I just have a look at this pipeline again, if I'm trying to say, well, I'm comparing two approaches, the one thing that I haven't been doing is just comparing it with the most simple thing out there. And the most simple thing out there would just be, well, let's just do no embeddings whatsoever. Let's just look at the words and the subwords, index all of those, get a weight for them, and that should be the simplest thing, right? Like, maybe that should also be included in this benchmark, because otherwise I'm just comparing neural networks with each other instead of just considering the really simple thing. Now, if I want to show you the effect of this, I also have to do something else, I think, because you can also wonder, the quality of this model that I'm measuring, that accuracy number, is that a function of the embedding, or is that a function of the data that's going in? Because I could also argue here, the more data that I give this thing, the better the model, right? And it might also be the case that certain embeddings are better in low data scenarios, and other embeddings are better in high data scenarios. And this little table is not showing me that part of the story. So what I'm now going to do is just give you a really cool use case for the Altair visualization library. Because what I've done, let's zoom out just a little bit, is I've reran the entire benchmark, but now I've taken a subsample at every time. So first I'm training with 500 examples, then 1,000, and then 2,000, then 3,000, etc. And you see the accuracy for the test set listed over here. Now, the cool thing about this Altair library is that you can zoom in, because if we are going to spot the difference between the fast text model and the count vectors, we are going to have to zoom in quite a bit. Yeah, so like really, really zooming in here, right? There's barely a difference between fast text and just doing count vectors. I am inclined to say we might have one example more, just by staring at this, right? But that's not even the biggest part of the story. One part of the story here is like, oh yeah, like really universal sentence encoders is doing a little bit better than just the basic count vectors, but not that much. But another part of the story is, you notice how much better we're getting just by adding more data? Another really cool feature about like being able to zoom in here is that you can look at this and you can kind of go, you know what? The slope here ain't done yet. There's still this delta y, delta x happening here. So if I'm going to draw any conclusion at this point, yeah, I can spend a lot of effort maybe finding an even more fancier model than a universal sentence encoder. And don't get me wrong, universal sentence encoder is amazing. There's a lot of stuff to like about that thing. But for this problem, it is a distraction. I should be getting more data. That's the only normal conclusion you can get when you look at this chart. And if I were to reflect now and say, well, that's not what this table says, then for a benchmark, it's too easy to be optimal in paper but broken in reality. And I see a lot of people nodding now, so that's nice, confirmation. But it's not even the most broken thing about this benchmark, because we've not talked about the data yet. So let's have a look at the data set that we're actually doing here. I have a subsample here of the data set, so you can get a bit of an example, right? So the text, will you turn the TV on? Okay, that's a label for smart home. That's a smart home command, right? Call an Uber for 2 people to go to 4th Street, all right? Uber, that's an intent. There's a thank you, there's a sync device, there's a credit card limit, there's how busy are you, there's translate. I don't know of a single virtual assistant in production at, let's say, a bank that also allows you to order an Uber or to like make I think you're also able to like throw a dice or something like this. So we are talking about this data set that has like 150 intents, but those are intents from like all sorts of different virtual assistants. And if they're all sorts of different virtual assistants, odds are that all those intents are mutually exclusive. So if I were an actual bank making an actual virtual assistant, let's say, questions about a debit card and questions about a debit card and credit card are really similar, but that's much harder than whatever we're doing here. So if I'm going to say anything general about the universal sentence encoder is great for chatbots, then I also have to recognize that whatever benchmark data set I have here, it doesn't match reality. It doesn't match whatever problem that I necessarily have. And this is true not just for this one benchmark, but maybe for pretty much every pre-trained model out there, right? And this is kind of an issue. It's getting really easy to be optimal on paper and to convince ourselves that we're really doing something that's clever, while we're really being sort of separating ourselves from reality. And this is, I think, a reason for concern. So I like to think this is a very general problem. And what I'm about to do is I'm about to draw a Venn diagram, mainly because it helps to shape the problem also for non-technical stakeholders. Because the way I look at it, and this is something I've definitely learned while working at Rasa, is if you're looking at a data science problem, there's kind of these two circles, and you're really hoping that they will overlap. Because on one end, you do have the stuff that you optimize. You have your models, you have your metrics. There's definitely a reason why we like doing analytical things, because it gives us a path towards optimization. But a big part of the danger here is that it doesn't necessarily overlap with stuff that our users care about. So if I'm helping out a team or a community member building their virtual assistant, people are usually surprised to learn that I'm really not that, I know my algorithms, but I barely talk about algorithms when I'm helping people. Usually I'm explaining this to them. The real trouble and the real hard part is ensuring that this overlap is actually quite big. And there's this guy on Twitter that I follow, and he basically has the best quote on this. A large part of this is that maybe the biggest impediment to enterprises getting value from AI today is that we've convinced the world that tweaking hyperparameters is prestigious, high-value work, and that curating a high-quality data set is tedious, grunt work to be outsourced, minimized, or automated. I genuinely feel this vibe. Follow him on Twitter, by the way. He's also my boss. But I really love this tweet, because it really does summarize what I think is a huge problem in enterprise today. I hear stories from consultants that say, I would love to have a look at my labels, but the person paying my check thinks I'm too expensive to actually look at the data, so we're outsourcing that to some person in a different part of the world, which feels really weird. And that kind of brings me to the second demo that I want to show you. So a lot of NLP revolves around sentiment. For some weird reason, whenever people go, oh, what's a use case for NLP, people always kind of go, sentiments, binary classification. And I get that. But I figured we should maybe do it properly, and I came across this data set from Google. The data set is called the Go Emotions dataset. Basically what they did is they scraped Reddit, and they basically have text like this, like, oh my god, yep, that's the final answer, thank you so much. There's a label gratitude, and there's a label approval. What's likable about this is that instead of saying it's a sentiment between 0 and 1, and we're going to reduce the dimensionality of human cultural sentiment into a single axis, we're just going to say, no, it's more complex. We're going to have a label for every single emotion. So confusion, remorse, surprise, amusement, disappointment. We're going to basically have a classification problem that's a lot like tagging. So it's not 0 or 1, it's lots of zeros and lots of ones, one for each emotion here. And I would like to stress, this is a data set that not only Google put out there, this is a data set, and also Stanford and Amazon Alexa, multiple people worked on this, but it's also one that they wrote a paper about. So there's effort being taken here that this is a good data set. And we can read a little bit about it. They took an effort that multiple people labeled a single row, but I will say Google is sort of putting this out there, which is giving me the impression, this is a data set that I can go ahead and use. This is something I can train models on. This is probably something that's nice and curated, useful, because emotion detection has a use case, I suppose. Then again, there is this other project called labelerrors.com. I recommend you go here daily. What this project is all about, and genuinely, the authors really did a cool thing here. They basically said, look, there might be mislabeled instances in ImageNet. There might be mislabeled images in QuickDraw or the Amazon sentiment data set. And if people are bragging about how state-of-the-art your model is, they're saying, hey, I have plus 2% on my test set, but the test set has 3% label errors, that'd be bad, right? Okay, so let's just look at a few examples. According to ImageNet, this is a bathtub, and this is a red panda. And I can scroll for a while, right? And ImageNet is a culprit. There's a paper attached to this project. It's a good read. There's an open source project called Clean Lab that's associated with this work as well. What's really interesting is that they also give estimates of how bad the label errors might be per data set. The authors estimate that QuickDraw has a 10% label error, 10. Amazon supposedly has around 2, right? That's also pretty bad. So then you start wondering, can I find bad labels in the Google Emotions dataset? Let's try some stuff, right? So this, I pre-made this, but I'm just going to try to so imagine I was doing this exercise at home, and I was just kind of curious, like, hey, we have this labelerrors.com argument. Maybe that's seeping into some data sets that I might be using, so it would be good to maybe just have a look. Like, we should care about this stuff, right? Like, if I'm responsible for the output of my algorithm, boy, am I also responsible for the stuff going in, right? Okay. So there's a few things in this data set, but I'm going to, because the data is from Reddit, I'm only going to zoom in on the excitement label of interest. Like, be careful with Reddit data. There's really a lot of garbage text on there. But we have a couple of examples here, right? So I have text here that's, labeled excitement 001, but there is some other stuff in here as well, because I also have a radar ID. This is the person who gave the label. Supposedly there's an identifier for that, that's in this data set. And the radar is also able to give it a very, to sort of state that the example is really unclear. Which is fair, right? Emotion detection is by no means like easy to label, so I think this is actually a really good practice, and I commend the authors that they've done this. But just from the sample, right? Like, I'm sure there are people who really enjoy being parents, though. Those people aren't us, and aren't most parents. I'm not sure if that's excitement. This is from sampling, right? I'm about to show you tricks that are better than sampling, but this already demonstrates that just sampling a couple of rows is already a good idea. I do agree with this, though. Okay, so what I do is I first say it might help to have a machine learning model around. The goal of this machine learning model is to help guide me. It's kind of like a chatbot, kind of, not really, but in a way. It's going to help me try to figure out which labels might be bad. And the reasoning here is, if I'm going to be fitting a model on a trained set and then using it on the trained set, it will be kind of weird if it wasn't able to predict the label correctly, right? Especially if it's like on a spectrum of high bias, high variance models, count vector logistic regression is really high bias. So like if the high bias model doesn't work on the trained set, something's up, right? That's kind of the idea. But it's also logistic regression in the sense that if you have the separating plane, you can also suggest that maybe all the points that are really close to that boundary, those are might be the points where there's a lot of doubt, where the model's really unsure what the label should be. So maybe we can also think about machine learning models not necessarily as models to predict something, but more as models that will help us label. And maybe there's also this avenue of work that we can consider where maybe if we have different models with different qualities, they will all have a different lens that allows us to look at data differently. So let's just see what happens when we do this. The first thing I'm going to do is I'm going to use the model uncertainty trick. If the predict proba value is like close to 0.5, it's binary, then I'm going to suggest like, okay, we should just have a look. So I have my logistic regression, I do my fit proba, and here's some of the examples that I get. That's adorable as F. It's not excitement. So this one I think, okay, there might be a cultural difference. This is twijfelachtig. Hè? So this could go either way, I think, personally. But then I see, oh my god, those tiny shoes, desire to boop snoot intensifies. and you know, so it is slang, right? Language is not necessarily straightforward. Someone who was labeling this might have had a different culture. We see that it was a very unclear example. But this, I relate to this so much, almost too much. I mean, there are also examples, and you're like, if there's a pattern, yes, that's not excitement, right? So it's, this is a proxy. This is not necessarily a guarantee or anything. But, okay. What happens if we do some other tricks? This is a trick I like to call short on confidence. The idea is that there is a correct label according to the data set. And if my model has like almost zero confidence that that's correct, that's bad, right? So I'm going to sort based on that. So correct class, if that has a really low score, I want to see those examples first. And the first example when I do this is, I'm inexplicably excited by name. I get so excited by how he curl passes. This is a very clear example, and it's not about excitement. The word excited is in the sentence twice. And I'm cherry-picking a little bit here, but then the second sentence is, oh my god, this is so amazing, keep up the awesome work and have a fantastic new year. And these are two people, apparently, who labeled it this way. And, you know, there's a bunch. Oh my god, yes, such an amazing combo. I mean, that could be excitement. This is kind of weird. Now, the cool thing that I will show you as a demo, which I think is really interesting, is right now I'm using the count vectorizer model, again, high bias, What I can also do is use an embedding model. Embeddings that are trained on Wikipedia use no count vectors whatsoever and just sort of say, well, what does that produce? Do I get different examples? And the answer is, yeah, you do. Like, you really, really do. If you do that, I'm using bypair embeddings now, you get these examples. Now, this is word embeddings, right? So these word embeddings have to be pooled together, which loses a little bit of information. So what is interesting to observe is that we tend to get the examples that are much shorter. We get not really long sentences, more like direct comments. But come on, wow, 3 exclamation points, that's not excitement. This is troubling, right? This is no bueno. Now, the clean labels data set that I just showed you earlier, sorry, the label errors, I should say, the authors of that also wrote this library called CleanLab. It contains a mathematically sensible heuristic to also find bad labels, which I recommend people. It's a cool library, it works. And what you can also do is just run that heuristic. It's a single function call. You feed it your probas, you feed it your labels, and then it will also sort of come up with a list of stuff that just deserves double checking. Now, I do want to add a little bit of nuance because I apologize for the quick scrolling, but you can also measure that different raters had like a different feeling about this one example. So I'm inexplicably excited by name, get so excited how we cope. That one example, I mean, there were 2 different raters who thought about it differently. So in a way, you could argue, hey, the data set also contains a little bit of doubt here. But how am I going to trust a model that's sort of trained on this, right? And also, just looking at everyone in the room, I think it's easy for me to say here because text is relatively easy to label, but I don't think it's a common industry practice to do this exercise. But for computer vision models and for text models, those are 2 really cool examples where you can assign doubt to your labels, and you can actually check, hey, am I even training on the right thing? Because if I'm talking about being optimal in paper and broken in reality, this is like villain numero uno, right? If we have bad labels in our data set and we are unaware of it, we're going to report super optimistic numbers and disappoint a whole lot of people if this ever gets to production. And, there's a reason why I do kind of want to talk about this. This is a screenshot from a model that's hosted on Hugging Face. Now, I should stress, Hugging Face is doing a lot of cool stuff. Non-English, they're doing a really, cool work. And I think it's nice that they have sort of a way for anyone to upload a model. However, when you look at the model card, it says there's 2 things that people will read. One of them is the example that you can run is I love AutoNLP. And the other one is that it has a pretty high accuracy score on the IMDb sentiment classification data set, which is probably going to make you think like, that's pretty useful. I might just go ahead and use that as a sentiment model or maybe fine-tune on it. And I cannot blame you if you do, because it's giving you reasons to put confidence in the model. But I hope we also agree, I cannot guarantee you that there will be no label errors on the data set that this thing was trained on. In fact, you can also wonder, like with the example before, maybe IMDb text differs from what people are doing in your virtual assistant. Maybe it's just a completely different set of examples. And how can I guarantee that even if you fine-tune, you're not overfitting on something else that's been pre-trained? You can also find the Google Emotions dataset on this platform, and you can have this little UI element to see all the different models that people have trained on it. I doubt, unfortunately, that they have done this exercise of finding bad labels. I think if you want to make this dataset properly clean, it's going to be a huge effort, actually. And I think we should care. Again, if I make this drawing of we have an actual problem that gets turned into an analytical problem and we're going to translate that back, and if I then see this development of it's going to be easier and easier, which is also kind of a good thing, that people can just fine-tune their models on whatever big data sets they can find, it's going to be really hard for me to understand what's actually in the model, right? And this is what if I have to sort of tell people what is Rasa really working on, like, yeah, we're doing research on algorithms, we want to have our stuff be super efficient, but a very large chunk of the research is actually going into how do we give tools to people for data quality. So things like, hey, you have an intent class that you're using inside of your virtual assistant, it only has 6 examples, please add more. Or, hey, there's a couple of examples between these 2 intents, seems to be causing a lot of confusion, could you please just verify and check? I could make the biggest investments that I want into more TensorFlow and like faster GPUs and stuff, but it's going to be meaningless unless this thing is sorted. And that also is kind of why I got hired. Like, they hired me with like a pretty simple mission. I am here to explain this sort of things to people. On YouTube, I host an educational channel where I explain how our algorithms work. Our most recent TensorFlow algorithm only looks for conversations where something unexpected happened, as in these are algorithms that will try to help you label. That's where most of our research really is going, and also all of our attention, because usually if there's a failure, it's there. We also highly recommend everyone to just, even if you're the senior data scientist, you have to look at the logs, what people sort of say to your virtual assistant. It's basically because of this. So what does that mean for the rest of us? Like, my background is NLP. I can imagine that's not everyone's use case here, but I do think that there are some general lessons that apply beyond just my own domain. I think that in general, we really should consider the effect of the training size more before we run a grid search. Grid search will typically give you this one number, but that one number is not going to tell you like the number of examples and that sort of thing. It's a huge dimensionality reduction of reality. I also think that it might be good to consider that a one metric might not reflect the complexity of reality at all. It's just a single number. You're going to optimize for one single number, but in reality, you're typically interested in like 5 things. Also, I think it's good to consider that pre-trained models might not reflect your problem, especially because they might be trained on wrong labels. I also would like everyone to maybe consider doing this finding bad labels exercise in their own data set. Moreover, though, I would like to consider that everything that I've discussed in this talk might just be the tip of the iceberg. I've not talked about fairness and bias issues. That's also a huge topic that we're going to have to talk about, right? So, the common thing in all of this, though, is that I think it's one thing to have a broken system, but it's even worse if you're blind to it. And that's the whole point that I'm trying to make here. I fear that it's getting really easy to download a pre-trained model with a very high number, that's going to give you false confidence, and that false confidence might just be the reason that you're not putting enough doubt in your own system. And that, I think, is a very legitimate concern that more people should think about. Speaking of which, I dabble in open source projects now and again, and I started looking at this label errors stuff, and I just started to think, well, if we're all going to be better looking for bad labels, it would help if we had like some great tools at our disposal to do this sort of thing, right? So as of yesterday, you can pip install DoubtLab. It is a suite of tools where the whole point is that it's easy for you to declare a couple of reasons why you might want to assign doubt to a row of data. The whole point is that you might have a couple of different models. Some of them might be text-based. For now, I'm mainly targeting the scikit-learn ecosystem. But the whole point is that you can maybe come up with 10 reasons why something might be off. Could be an outlier, let's say, right? And then we are just going to handle the sorting such that after a couple of minutes, you just have a list of examples that deserve to be checked first. The API is relatively simple. You just assign a doubt ensemble. You can make keyword arguments or a dictionary where you just give a name to a reason. You can have a reason for proba, that's like the low confidence, close to 0.5. Give it a machine learning model. You can have more than one of these. You can have multiple models. All that stuff works. You could also say if there's a wrong prediction, that's also a reason. And I can give you either the indices of all the rows as you double check, or a data frame of predicates that's sorted, which will also tell you all the reasons why. I hope this is super exciting. That's a QR code, so if you want to check out the GitHub repo, you can totally do that. This is stuff that I'm working for on behalf of Rasa as well. My employer would love to tell you that we're hiring, but moreover, ask me anything. I'd love to hear. I would love to get more feedback on this. I am going to work on this year, so please check this out. Thanks for listening. Who wants to catch the cube?
Got it. Thanks for your talk. Awesome that you also have a library available. I think it was very exciting, and I have a question about the excitement example. So the thing I'm wondering is you showed some of the labels in the beginning, and then you showed basically all the misclassified excitement examples. I wonder what labels did they get classified as? Maybe there's like something like joy.
Could you repeat, which labels did they? Could you repeat the question?
So the question is, what labels did they get assigned? Maybe they're like joy or happy or something that's very close to excitement.
So the paper actually lists that there is a bit of correlation. So there's like emotions that are a little bit more on the positive side of the spectrum, so to say, and they tend to correlate a bit. So joy and excitement are more common than excitement and anger, for example.
Yes.
So that can also be used to find bad labels, of course. So the thing is, I would love to show you some examples, but this is Reddit data, so I prefer to do that when the camera is off. No, because it's Reddit, there really is some horrible stuff in here that I'm not comfortable putting on YouTube.
No, okay.
But please come to me afterwards. I'll gladly show you some details if you like.
Okay, but I guess also part of the answer is like every emotion can be 0 or 1, and you can have multiple also.
Yes, yeah, it's tagging. Okay. It's not classification. It's tagging.
Yeah, okay.
Yeah,
okay,
yeah.
That answers my question also.
One thing I should also emphasize here, that's actually good to mention. Sentiment is a really weird use case when you think about it, right? Because it's so opinionated and so determined by culture. And also, I think sarcasm detection is an unsolved problem. So how on earth can sentiment ever be solved, right? If we cannot detect sarcasm, we cannot detect emotion. If we cannot detect emotion, we cannot do sentiment. It's an incredibly hard problem. That's also a lesson I've learned from doing this.
Thanks.
There's all the way in the back. Whoa.
Thanks. It was a fantastic talk, and I can relate to that so much. Yeah, so I wonder, you presented the repo, right? Doubt Lab, right?
I mean, it's live since yesterday, so yeah,
Okay,
cool. It is fresh off the press in that sense.
So I was wondering if you think it's something that can be already operationalized, or it's still kind of in the research phase, in the sense, is it mature enough, kind of the field of, yeah? Well,
okay, so I made this, it's live since yesterday. Like, please don't bet your company on it, right?
Yeah, sure.
Single dude here. Having said that, this is not meant to be run live. This is meant to be run on your offline data set.
Yeah.
So, and to be honest, I think it's better to use this as a reason to actually look at your data.
Yeah.
And to maybe help you sort what to look at first. Everything from there is something that the library won't solve for you. That's something you have to do because it depends on your problem, which you will understand better than this for loop ever will.
Yeah, so maybe let me rephrase it. Let's say I do this, of course I do it on my data, I want to understand a bit. And so do you think that kind of you can cover already a large number of use cases with these, or is there something that you think you can add in the future, let's say 1 to 2 years, or is there something that the machine learning community still has to develop in order to get more understanding?
So there is some fairness in it. So you are right that I do think there's a weakness in this approach. Namely, what could happen is that I'm going to present you with examples to look at, and then people are going to go, I checked those, done. That's dangerous, right? Because these models will have blind spots too. You're going to train on bad labels, and then you're going to use a model trained on those bad labels to have less bad labels. But it really depends on how bad the labels were in the first place. So, and also if you're using word embeddings, those are biased too. So there's all sorts of things that may or may not work. What I will definitely say is there's tools available now that are super useful. I am eagerly asking everyone here to give me feedback. Because that's also the cool way about the way I can do research. I don't have to work, I get to work with a community instead of working with a static data set. So if all of you tell me, hey, I've eyeballed it, this works better than that, that's great. Now, in terms of plans for the future, there are 2 things that I do have in the back of my mind. This works really well for X and Y kinds of situations, so scikit-learn, maybe image classification. Entity detection, not so much, because that's a nested data structure. And also finding, like, where is the garbage bin in this photo? Maybe there's 2 of them. So that's going to be a bit awkward with this API. I might want to make a separate ensemble for that. Mm-hmm. Another thing that I've also been thinking about is, this kind of reminds me of Snorkel a little bit. You could look at this reason and say, that's kind of like a weak business rule. We might be able to do something clever with aggregating that, instead of just looking at overlap. That said, though, if this thing is going to tell you, look, these are outliers, if you check those out, I would argue that's a good idea. Yeah. Now, how you're going to do outliers depends on your problem, but I think there's already enough in here, and there are unit tests, that it's worth for people to do the exercise. But it's not done forever project. This is something that definitely requires a year's worth of time, I think.
Cool. Yeah. Thanks.
There's 1 person left, I think. And I'm also here like during the break, right? So don't worry. If you want to see demos.
Hi, Vincent. Thank you for the talk.
We should switch. We should switch.
Okay, let's do
Oh, okay. Final question. After that, there's going to be a break, but I'll be here. Final question, yeah?
I mean, by checking these wrongly labeled dataset, I mean, at some point, do you think we would be throwing away the culture from the dataset?
We're throwing away the what, sorry?
By checking these wrong labels in the dataset, at some point, do you think we'll be throwing away the culture from the model?
So the question is, are we going to throw away the culture from the model? The most reasonable thing I can say on the spot here is you got to be careful with culture, right? That's a good thing to be aware of, but it really depends on your application as well. So to answer your question fully also depends a lot on the application, and if I have more context there, I might be able to give you more pointing advice. I do agree that a lot of this NLP stuff is really tricky because language is cultural. But that makes the whole field super complicated. Language is not a bag of words. But I do think it would be good to put more doubt in these systems, and that's what I'm trying to achieve here. You could also go overboard. That I agree with. Yeah. So we do have time for your question. All right. All right. Let's go, Ruben.
Would you actually drop out the outliers, or would you reject the whole data set? Because that's a different thing. This is just a toolkit that is customizable that will allow you, hopefully, more easily to find weird things in your data set. What you do with it depends on you. I don't try to be opinionated in terms of what you should do with when you find weird examples. That really depends on your use case as well. So that's responsibility that I would like to pass on to the data scientist. Okay, now we really need to switch.
Right. All right.